All right, so for the dynamics unit, okay, we'll go over again the key concepts, the things that are going to be big on the final, okay, all of that kind of stuff. So, let's say we're looking at a question like this. A 60 kilogram box is being pulled by 2 ropes across a frictionless surface. Okay, rope 1 pulls due east with 200 newtons of force, and rope 2 pulls 50 degrees north of east with 300 newtons worth of force. What is the acceleration of the box? Okay, could easily get one like this. Okay, on your final exam, it is a Newton's second law problem involving vector addition. Okay, give you a couple of minutes on that one, see how you do there. All right, so as we said, Newton's second law problem using vector addition. Okay, what's the first thing I should draw? In a Newton's second law problem, we always draw what first? A free body diagram, okay? Which is going to show the 2 forces acting on the box, their magnitudes and direction, okay? And I don't know if I have that here, but it looks like I took it off. Okay, so we start out then with this. Okay, we've got our box that had a mass of 60 kilograms. Okay, and it's being pulled due east by 200 newtons. Okay, and then 300 newtons, 50 degrees north of east. Okay, so there's my free body diagram. Now, I know I've got these 2 forces, so in a vector diagram, okay, I need to represent them separately, which is the next thing I need to do. So I'm going to have my 200 newtons. Okay, and then I'm going to have the 300 newtons. Okay, 50 degrees north of east. So this will be y, this will be x. I am going to bring all that a little bit further down so it's not into the writing there like I made it. All right, so that means then that my net force is going to go from here to there. Okay, that is going to be my net force. I'm going to draw the triangle outside just because I don't want it to get messy, but you could have drawn it right on top of the other lines as well. That'll be totally fine. All right, so this will be F net. Okay, this will be the X component of F net. This will be the Y component of F net. This will be the vector of F net. If you drew it the other way, you're still fine. If you drew it right over top of this stuff, totally fine. Okay? All right, so here's what I've got to do then. I've got to find all the X's and Y's, just like I would in any other vector addition question. So to find green X, okay, that is going to be the cos of 50 degrees times 300 newtons. Okay, so 192.8 newtons east. Okay, the Y component is the opposite side, so it will be the sine of 50 times 300 newtons. Okay, so 229.8 newtons, and that is north. Okay, so now I've got all the information I need to find my purple triangle for my F net. Okay, so purple X is going to be 200 plus 192.8. So purple X is going to be 392.8 newtons east. And I'm just going to make sure I get that in my calculator, excuse me, with all the decimals. Okay, so now I've got that. Okay, and then my Y component is just the 229.8. That's the only time it goes north, so I don't need to do anything else with that one. This side here is already 229.8 newtons. All right, now that I've got those 2 things, I'm going to get the magnitude of my net force. Okay, so I just use Pythagorean theorem, okay, to get the magnitude of F net. All All right, so it'll be the square root of 392.8 squared plus 229.8 squared. Okay, 455.12 newtons. Okay, I need to get that angle. If you get the complementary angle, that's totally fine. Okay, I'm just going to go 10 to the minus 1 of my opposite side, 392.8, divided by my adjacent side, 229.8, okay, to get my vector. And so second 10 of opposite divided by adjacent. All right, so I'm getting 59.67 degrees. Okay, and for me that is east of north. All right, now I've got net force. What did the question want? Acceleration. Okay, so that's where Newton's second law comes in here. F net equals mass times acceleration. Okay, so I'm just going to divide both sides by mass to get the acceleration. Okay, so that'll be our 455 divided by 60 kilograms. Okay, so there's our acceleration. We only have 2 significant digits, so we're looking at 7.6 meters per second squared at 60 degrees east of north, or at 30 degrees north of east as our final answer. Okay, would that be an exam level question with one of them being horizontal and one of them being angled? That's typically what I've asked in the past. Okay, so key things in the dynamics unit. You're probably going to see something to do with Newton's first law in the multiple choice. Okay, understanding that, you know, in the absence of a net force, an object travels at a constant velocity. Okay, things like that, and then maybe a couple of things about maybe the effective mass. Like on your unit exam, you had the shopping cart question. You know, what would happen if I keep throwing cans of soup in the shopping cart? What would happen to the acceleration? Well, it would go down because the force is remaining the same and the mass is increasing. Like stuff like that in the multiple choice. Okay, but you're going to get more calculation-based stuff like this. Okay, in the written response. All right, other things from dynamics after we did Newton's second law, and we're going to do a few more Newton's second law examples today. Okay, then we went on to work energy theorem. Okay, so when you force times distance equals the change in mechanical energy, and you had to calculate various things about, you know, the speed or the height or whatever. Okay, and then you had law of conservation of energy, which was the same as science 10, a roller coaster question or kid going down a hill in the absence of any non-conservative forces like friction. Okay, calculating speed or height, okay, at those various places, and that was it. Okay, and there were really only 4, well, Newton's third law, so there's not going to be any 2-box questions on your final. Okay, like what was on your unit exam. Expect there's probably going to be a multiple choice question about Newton's third law. Okay, but I'll double check. I'm pretty sure I didn't put a 2-box question on your final, but I'll double check before the end of the day today. I'm pretty sure I didn't do that. I had a gut to do it, and then I think I checked that gut, okay, to make sure that I didn't. So I'll just double check. Okay. All right. While I'm double checking, see what we remember about this kind of situation. I am looking for the tension in this wire if this angle here between the 2 wires is 100 degrees. So for this question, this is what we call a static question. Okay, what's the net force in this question? 0. Okay, the mass isn't moving, it's suspended by 2 cables, which do what with the weight of this 100 kilogram mass? They split it. Okay, now the weight of this 100 kilogram mass acts directly downwards and is 981 newtons. Okay. Now that means that these cables have to produce an upward force between them of 981 newtons. That means each one of them holds half of that. Okay, so if I do this and I make, whoops, I went too far up, and I make a triangle for this cable here, okay, it's going to look like that. This angle will now be 50 degrees, okay, and I know that this side is half of 9.81, which should be 490.5 newtons. Well, now that I know one side and the angle, can I find the hypotenuse? Okay, so it's kind of vectors, okay, but it's also recognizing a question in which net force is 0 because all the forces cancel out. So that's kind of our free body diagram. This is kind of the vector diagram here, this triangle that we've drawn, okay, but in the end, to get the tension in the cable, all I'm doing is saying that this is my adjacent side, and I'm looking for the hypotenuse. Okay, so I would say the cos of 50 degrees equals the adjacent side, 490.5 newtons, divided by the hypotenuse, okay, which is the tension I'm looking for. So the tension will be 490.5 newtons divided by the cos of 50 degrees. Okay, and that'll give me the tension in that cable. Okay, so we have 3 significant figures there, so 763 newtons. Okay, I don't need to put a vector on that because it's tension, and tension pulls both ways. Okay, is that ringing a bell? Okay, still a vector question, still a Newton's second law question. Okay, got this box here. Okay. At the bottom of the ramp, it is moving at 3 meters per second. An applied force of 500 newtons pushes it up the ramp that is 20 meters long. Okay? When it is at the top of the ramp, it is 10 meters higher than it is at the bottom. I want the speed at the top of the ramp. Incidentally, this is about the top of the heap in terms of difficulty for this type of question. There is a long way and a short way to do it. I encourage you to do it the short way, because I shall not wait for you to do it the long way. Okay? Plus final kinetic. Okay, so work energy theorem. This is the change in mechanical energy. Now, are any of those 4 forms of energy that I just wrote down, are any of them 0? Initial potential, because we're at the bottom of the ramp. There's no initial height. Okay, so this one I can take right out. All of the initial energy is kinetic, this 3 meters per second, okay, that the box is moving at the bottom of the ramp. Okay, now what I'm looking for is the final speed of the box. Okay, so that's near the top there. That would be part of my final kinetic energy. Agreed? So what I want to do right now is isolate that. Okay, before I start putting in a whole bunch of other variables, let me isolate final kinetic energy. Okay, so right now that means I'm going to subtract EK initial over here. So I'm going to have force times distance minus initial kinetic plus the final potential. Okay, that's going to equal my final kinetic. Everybody okay with that? Okay, so now I'm going to put in more of the data that I have here. Okay, so I'm going to put in that I'm going to leave this as force times distance. I'm going to expand these out here to their actual formula. So force times distance minus, okay, 1/2 mvi squared plus mgh final equals 1/2 mv final squared. Okay, I'm looking for v final. What do I do with the half and the m? Divide them over to the other side. I want VF, not VF squared. What do? Square root the whole thing. Okay, so now I just need to plug in my numbers. I have all of the numbers I've listed here. I know the force is 500 newtons. I know the ramp is 20 meters long. Okay, I'm going to subtract from that the initial kinetic energy, which is 1/2 times 100 times 3 squared. And then I'm going to add on to that the final potential, okay, which was 100 times 9.81 times 10 meters. Okay, and then I'm going to divide that all by 1/2 times 100, okay, and I'll get the final kinetic energy. Or sorry, the final speed, not the final kinetic energy. Okay, so square root, okay, of, actually let's do this piece by piece, that's probably smarter. 500 times 20 minus 1/2 times 100 times 3 squared plus 100 times 9.81 times 10. Okay, and then I'm going to divide that by 50. And then I'm going to square root that. Okay, so at the top of the ramp, this thing's moving pretty fast. Okay, moving at 19, well, we only have 2 significant digits, so 20 meters per second. Okay, that's the short way. Okay, work energy theorem is the shortest way to do this. How many people started doing an inclined plane problem using the angle and all that? Okay, you can do it that way. Okay, you can do this as an inclined plane, find the acceleration. Okay, if you're doing it that way, then basically you're doing this. You're doing this as a Newton's second law problem. Okay, you're saying you have an applied force of 500 newtons up the ramp. Okay, you're going to have F parallel going this way. It doesn't mention friction, so we can avoid having any friction in there. Okay, calculate the force of gravity, calculate F parallel. Okay, go 500 minus F parallel to get the net force, and then from there calculate the acceleration, and then from there use the 20 meters and the initial velocity and do an acceleration calculation where you get finally the final speed at the top of the ramp. I'm out of breath just talking about how you would do that one as a Newton's second law question. It's a lot more work. Will you arrive at the same answer? Yes. But if you do that on a final exam, it will take you 4 times as long to do it that way as this way. Okay? The work energy theorem was really like what? 3 steps at the most. Okay, but I have to recognize what kind of question it is. Now, it's not to say it is not completely legitimate to do it as a Newton's second law problem. It is. Just saying it takes longer. A lot longer. Okay, and I wouldn't want you to do it that way. Now, on your final exam, I probably wouldn't give you the hardest one. I think we had that discussion the other day. Probably wouldn't give you the hardest work energy theorem question I could think of. But I'm going to give you a work energy theorem question. It's an important concept. Okay. Any questions on that? Because that's tricky. What else we got here? Okay, that's a Newton's second law problem. Spoiler alert. It's a Newton's second law problem. This one, feel free to do all that F parallel stuff you were doing on the last one. Okay? It'll be a lot easier to solve this one that way. Okay? Give you a couple minutes on that one. Okay, so on this one here, we do have a Newton's second law problem. Okay, so kind of our free body diagram needs to look like this. Okay, this will be the force of gravity, which is going to be 1962 newtons. Okay, 200 times 9.81. Okay, this is going to be F normal, which for this question we're not going to need. Okay, and then we're going to have this side here, which is F parallel, which we are going to need. Okay, and then this angle here is 30 degrees. All right, so forces I need to identify. This thing is sliding down the ramp because of F parallel. It is being resisted because of friction. Okay, question wants me to figure out what's the force of friction. Well, right now I know the mass and the acceleration. What can I find? Net force. Okay, and that's probably something I should find, as it's usually pretty important. Okay, mass times acceleration, so 200 kilograms times 1.7 meters per second squared. All right, so my net force is 340 newtons, and that is down the ramp. Okay, because it does tell me it's going down the ramp. All right, so 340 newtons down the ramp is my net force. That means that that is the vector sum of F parallel and the force of friction, because they are the two forces that are acting here. So if I can find F parallel, which I can, it's the opposite side of that triangle. So that'll be the sine of 30 times 1,962, which oddly enough will come out to 981 newtons. Okay, 981 newtons. Okay, so now that I know that one, and I know what that one and friction add up to, can I find friction? Okay, so my force of friction, okay, will be F net minus F parallel. Okay, so 340 minus 981. Okay, gives me negative 641 newtons, or 6.4 times 10 to the 2 newtons up the ramp. Okay, very typical inclined plane question. Okay, would you lose a mark if you didn't write up the ramp? You absolutely would. Force is a vector quantity. Okay, all right, did we do a whole bunch like that in class? Like countless numbers of inclined plane questions in class. Okay, that one is really no different than any of them. Okay, and it's about middle of the road in terms of level of difficulty. Okay, could have made that one tougher by adding on, instead of find the force of friction, find the coefficient of friction. Okay, if I'd have done that, then you would have actually had to find what was F normal, so the other side of this triangle. Force of friction divided by F normal, and got the decimal, got that coefficient of friction with an added step. Okay, that would have made it a little more involved. Okay, see what we remember about systems. Okay, I want you to tell me the acceleration of the 2 kilogram mass if there is 4 newtons worth of friction resisting the 2 kilogram mass, and this is decimal 750 kilograms over here. Okay, give you a couple minutes on that system. Okay, so first thing we got to do is calculate the other forces involved. That would be the force of gravity on the 0.750 kilogram mass. Okay, so we'll go 0.75 times 9.81, and we'll get that driving force of 7.35 newtons. We'll keep all the decimals. Newtons here. Okay, and those are the only two forces acting. So if I want to calculate the acceleration, okay, I just have to find the net force. All right, so F net is going to be 7.3575 minus 4 newtons. Okay, because they're acting in opposition to each other, so that's going to give me a 3.3575 newtons, if my mental math is correct there. Okay, that net force is actually acting on 2.75 kilograms worth of mass, the mass of the system. So if I take that, so if I go minus 4, okay, and then I divide that by 2.75 kilograms, that tells me both the acceleration of the system and the acceleration of the 2 kilogram mass, except that I have to put we only have one significant digit there, don't we? We'll say it's 2. 1.2 meters per second squared forward. Okay, or right, or along the table, or some other vector, because they did ask you about only one of the masses. Had I asked you for the acceleration of the system, then you couldn't have put a vector in, because one is going down and the other is going across. Okay, ringing a bell? Okay. So there could be a system question, okay, on your final exam, okay, that you'd have to remember that the masses combine in that type of question form. Okay, let's see what we remember about this kind of question. So we have a 10 kilogram mass at the top of a frictionless incline. It is moving at 4 meters per second. A little while later, the same 10 kilogram mass is at the bottom of the incline, moving at 16 meters per second, and its height above the bottom is 10 meters. I want to know how high it was at the beginning. So it's a conservation of energy question, so we got EI equals EF. Okay, at the beginning, we have both types of energy, so we would have initial potential plus initial kinetic equals final potential plus final kinetic. Okay, what we're looking for is part of the initial potential because we're looking for the initial height. So we would subtract EK initial over to the other side. So we would have this. Okay, and then we just plug in all of our formulas. So MGHI equals MGHF plus 1/2 MVF squared minus 1/2 MVI squared. The m's are going to cancel even though it was given to us. And then we just divide both sides by G to get HI. Okay, so HI will be 9.81 times 10 plus 1/2 times 16 squared minus 1/2 times 4 squared. Okay, divided by 9.81. Okay, so the initial height's 22 meters. All right, ringing a bell. That's basically all the stuff from Unit 2. Okay. Conservation of energy, work energy theorem. We did several Newton's law questions, including a system question. Okay, we did Newton's law questioning that involved vector addition. Okay, that's what you're going to see. And as I said, the test does not, the multiple choice sort of goes in order, but the written response, it's all over the place. Okay? Some questions are involving multiple units, and because I didn't really pay attention to what order I was putting the questions in. Okay? So the written response kind of jumps all over the place, so you have to do a good job of figuring out what type of question it is based on what you were given and the context of the question. Okay? Did I tell you how many questions are going to be on there? I did already, right? Okay. Okay, so we have 21 multiple choice and 12 written response. Okay, so it's the multiple choice part's pretty short. In fact, you only have to do kind of the most simple calculations, really. Any calculations in there are very, very simple. And then we've already talked about kind of what's in the written here. Okay, so I mean, nothing you haven't done before. I'd say there's one question that's probably going to be a bit challenging, but it's nothing you haven't done several times already. Okay, but it's kind of in combination with a few things, so that might prove it to be a bit difficult. Okay, gives you a pretty good idea. How many people have started doing the review package? Okay, I mean, I know this test is your last one. It's a ways off yet, so you're probably prioritizing other tests right now, and that is fine. Okay, just know you do need to get at it eventually. Don't put it off till the night before, okay, or it'll prove to be too much for you. Okay. Oh, and you guys, for writing your exams, okay, I think I told you this already, but you guys are writing in St. Maximilian, okay, which I believe is the last one on the left in this wing. And yeah, so that's where you need to go on the morning of the 29th to be there for 8:45. Okay, remember all you need to bring with you is a few pencils and your calculator with good batteries in it, and a drink and a snack. Okay, that's it. Everything else will be provided. The back page of your test is the formula sheet, so you can tear it off. Okay, and you'll have that. You'll be set to go. There'll be a multiple choice form, same as always, a little half sheet. Okay, if you're to write the multiple choice answers in. Okay, so all familiar stuff to you. And normally, you guys, if you normally write in learning support, obviously go straight to learning support. They will have your tests ready for you as well.